All right, so these are called abbreviated electron configurations. And abbreviated electron configurations still represent the same exact thing. We're still looking at the arrangement of the electrons, but we're just able to write it in a little shorter version. So we can abbreviate an electron configuration with a noble gas. So first of all, you need to know what a noble gas is. Right, where are the noble gases found? The very end, group number what? 18 or 8, right? Sometimes we label them 1 through 8, and sometimes we label them 1 through 18. The noble gases are found in group 18, all the way at the end. And what's special about noble gases?
They have a full outer ring.
Perfect. They have a full outer shell. So now that we know what shells are, right, we know that that makes a little bit more sense to us now. Think about this. A noble gas, like for example neon, its electron configuration is 1s2, 2s2, 2p6. So if it's going to add another electron, it's got to open up a whole other shell, right? When we say full outer shells, that's what we're talking about now, right? Its p orbitals are full. So I want to go ahead and start with an example here, and then I'll show you how to abbreviate. So let's find the, can you guys see that in the back? Okay. Let's do the example for calcium. Let's do an example for calcium. And do the full electron configuration for calcium, and then I'll show you how to abbreviate it. So calcium, our electron configuration would be, someone want to read theirs for me? Felicity, go. What you got? Okay, good. But I need the full thing. Yeah, Kevin, go. (4s2). Good, right? So when we say electron configuration, we do want the whole thing unless we say abbreviated. So here's what our electron configuration for calcium looks like. Sorry, I'm trying to make this happen here. All right. Now, in order to abbreviate this electron configuration, we need to find the noble gas and the energy level before calcium. So look on your periodic table. What's the noble gas that comes before calcium?
Argon.
It's argon. Okay, so what we do with abbreviating our electron configurations is we say, well, doesn't calcium look exactly the same as argon up to that point? And then it's just a couple more, right? So the way we abbreviate it is like this. If I'm looking at the electron or the abbreviated electron configuration for calcium, we say it's the same as argon plus 4s2. Right? That's it. Because the electron configuration for argon is, let me get ours back up here. Here's our total electron configuration underneath, okay? This is calcium's full thing. 1s2, 2s2, 2, okay, all that stuff. Doesn't argon look the same to here? To 3p6? Yeah. So when we abbreviate it, we say it's the same as argon plus whatever comes after that. Okay? That's it.
So you're trying to find, to abbreviate it, what it looks like?
We're just abbreviating it so we don't have to write out the whole 1s2, 2s2, whatever.
Wait,
Just makes it smaller.
Wait, why do we have to do argon instead of like a different element?
So why couldn't we just use like potassium? Right? Because potassium comes right before calcium. Mm-hmm. The reason we can't is because we have to use elements that have a full shell. And the only ones that have full shells are the noble gases. Okay? Here's a couple caveats with this. You can't abbreviate a noble gas with itself. So let's say I had asked for the abbreviated configuration for krypton. You can't just say krypton in parentheses and call it good. Right? You can't abbreviate something with itself. So you would have to go argon, and then you'd go 4s2, 3d10, 4p6. Okay? So let's look at another example here. Let's do iron, Fe. Okay, iron is located in 3D. So tell me the noble gas that comes before that. Yeah, still, it's argon again, right? So I'm looking for iron.
Why isn't it the 4s? Why isn't it 4s2?
If I'm going to abbreviate this, I'll say it's the same as argon, but then I can't just do 3D something. I have to finish it. So, right, I've got to go from argon. After argon, in order to get to iron, I have to go 4s2. Then I need to go 3D, 1, 2, 3, 4, 5, 6. Right, so there's my completed abbreviated electron configuration. Right. Okay, so if we're looking at strontium, the noble gas that comes before is krypton, then 5s2. Okay, how are we feeling about that? Good, good, good. All right, try this last one on your own. Te, tellurilium. Tellurilium's in 1, 2, 3, 4, 5p. In order to check ourselves now, we need to think about how many electrons are found in this krypton. Right? Krypton contains 36, plus 2, plus 10, plus 4. Right? So 36 plus 4 is 40, 50, 52. Is that how many tellurium I'm supposed to have?
Yes.
Right, 52. Okay? So if we want to still check yourself, you can. You're just looking at how many is contained in krypton, and it's atomic number 36. And then we go 5s2, 4d10, and all that kind of stuff. Okay? What would happen if I asked you to find the electron configuration of an ion?
It don't work.
It works. It works. Let's find the abbreviated configuration of O minus 2. Okay?
Oxygen?
Yep. Oxygen with a minus 2 charge. So let's think about this. If oxygen has a minus 2 charge, does that mean it has 2 less electrons or 2 more electrons? 2 more electrons. Because a minus 2 charge means I've got 2 extra electrons, 2 more negatives than normal. So if I've got 2 extra electrons, now instead of looking exactly like oxygen, what does it really look like? It really looks like neon. Right? It doesn't behave like neon because its protons are not adjusting, but its electron configuration would look similar to that of neutral neon. Right? So if I was doing O minus 2, I would say, if I'm going to abbreviate it, okay, that's kind of silly, but helium plus 2s2 2p6. Right? O minus 2 would have 10 electrons, and so this is 2 plus 6, which is 10 electrons.
This is finding the what?
Same electron configuration, but instead of being neutral, now I've got 2 extra electrons on oxygen. And so if I've got 2 extra electrons, that means I have 10 I have to represent, and so it looks something like that.
Wait, why?
It's just as an extra example, if I asked you to do it of an ion rather than a neutral one.
So why are we talking about neon?
Yeah, you can. You could. If I gave you this and I told you find the element, I would have to tell you find the neutral element. Right? That's a good question. Yeah, really good.
Because oxygen can't go.
Yes. Good question. Okay, so Brady asked if it was oxygen plus 2, that means it had 2 less electrons, and it would behave, or it would look like the electron configuration for carbon. Okay?
Oh.
All right, very good. Get back with your partner. We're going to do a couple more from that sheet, and then we're going to move on a little bit. Yeah.
On that one, when you're P, so if you're from here, wouldn't you go to 2s2, but if you're trying to get to oxygen, when you get 2p4 instead of 2p.
Okay, yeah, usually, if we were doing regular oxygen, it would be 2p4. But since we have charge of -2, that means we've got 2 more electrons than normal. So that adds 1, 2. Yeah.
So if it was like a -3, it would go to
So
it would go
It
to
would look like
sodium.
sodium. Yeah, good.
what if I was
And if it was a +2, you'd go back to. So it's got 2 less electrons than normal.
Okay.
So if it's a positive charge, it's actually
It's got less
back.
electrons.
What numbers are we supposed to do?
Okay, on the sheet, let's do numbers. Let's do 6 and 13. 6 and 13. 6 and 13. I want to do one more. 17. 6, 13, 17. All right, so in orbital notation, we're going to have a situation where we draw out our individual electrons. Okay, and so if we see a line with nothing on it, that's considered an unoccupied orbital. It means it has no electrons in it. That's it. If we see a line with one arrow, that means it's got one electron in it, right? That's how we represent electrons, is with this arrow. And I couldn't get PowerPoint to do it, but you'll see most of them really represented with like this half arrowhead, okay? So you'll see an electron really kind of drawn like that, okay? Or this, and we'll talk about the difference here in a second. But electrons are typically drawn with like this half arrowhead on them. So if I see an orbital that has nothing on it, that's unoccupied, has no electrons. If I see one with one, that means it's got one electron. And if I see with two electrons, we're going to have one of our electrons facing upward and one of them facing downward. That has to do with what's called electron spin. Okay, and we'll talk about that here in a second. But essentially what's going to happen is we're going to be able to take our electron configuration and represent it in a diagram that we can see our individual electrons. Okay? So this drawing of the electrons is called orbital notation. And I will just tell you over and over again, year after year when I do this, I'll ask you to write the electron configuration and inevitably people will draw the arrows. And that's wrong. Right? Electron configuration is the 1s2, 2s2. Orbital notation is the drawing of the actual electrons. Okay, so I'll keep reminding you of that. All right, so when we're writing out our orbital notation and when we're drawing out our electrons, we follow what's called Hund's rule. Okay, and all that Hund's rule says is that orbitals that have equal energy have to be occupied by one electron first. All of the orbitals have to have one electron first before you can go back and put the second electron in. Okay, and that'll make more sense here in just a minute. But we have to fill our electrons in basically evenly. Right? We fill them in evenly rather than filling them a little bit at a time. It's kind of abstract what I'm saying right now until we actually see a visual. But we have to fill them in equal energy levels first, and then we can go back and add the second one. All right. Any electrons occupied in a singly occupied orbital have to have the same spin state. The same spin state. So when two electrons are found in an orbital, right, because an orbital is allowed a maximum of 2 electrons, when they're found in an orbital, one of them has to be spinning in the positive direction and the other one has to be spinning in the negative direction. Okay, and so we represent that with one arrow pointing upward, one arrow pointing downward. That will represent the spin states of the electrons. So as we're writing out our electrons, we're always going to put in that positive spin state electron first. And then after that, we'll be able to fill it in with a negative spin state electron. Okay? So as we're filling these in, we're going to put our positive spin state electron in first. All right. Let's look at an example for nitrogen. I want to go ahead and just draw. I want to show you the example first, and then I'll kind of show you how we got there. Okay, here's an example for nitrogen. Okay, nitrogen's electron configuration is 1s2, 2s2, 2p3. Okay, so as we go over to look at the, As we go over to look at the diagram of it, you'll see that here's the 1s electrons. There's 2 of them, right? Here's the 2s electrons. There's 2 of them. Here's the 2p electrons. And here's where you see Hund's rule applied. As we filled in the 2p electrons, we didn't go 1, 2, 3. right? That's not what we did. Let me make that a little darker color so you guys can see. We didn't go 1, 2, 3. Okay? Instead, we fill in the electrons 1, 2, 3. If we would need another one, we'd come back and go 4, 5, 6. Right? But for nitrogen, we don't. We only need 3. Okay? So here's how it works. You fill every energy level one at a time. I filled the 1s orbitals. Then I moved on to the 2s orbitals. Then I move on to the 2p orbitals, and that's where it gets a little bit more intense. Okay? Let's try orbital notation for boron first. Okay? Let's try boron. Yeah, Hamilton. Right. Yep. So we're going to get into the pattern of filling the orbitals across and then coming back and putting in the second one so that we know that we're doing it right every time. So boron is 1s2, 2s2, 2p1, right? Do you see where boron is? Sometimes I like to just write out what I'm kind of aiming for here, right? Boron is 1s2, 2s2, 2p1. You don't have to have the configuration written out. It just helps me kind of get a clear picture. All right, so now we go into the actual orbital notation part, and that means we actually just draw the lines for the orbitals. This is my 1s orbital. This is my 2s orbital. And then how many, I'm not drawing them like boxes like they did for nitrogen. You don't have to have them in boxes. Just the line is fine. Okay? I want to draw my orbitals first, then we'll go back and add the electrons. So now I need to draw the p orbitals. How many versions of the p orbitals are there? Okay, there's 3 versions. So here's the deal. I have to draw all 3, even though I know only one of them is going to get an electron, right? I understand that it's 2p1, but you still have to draw all 3 versions of the p orbitals. Remember how at the very beginning we talked about how there was px, py, pz, they were on the different axes? We showed them drawn like that, right? There's 3 versions of the p orbitals, so you have to draw all 3. But as I go add my electrons, I'm gonna do them in this order, and this is important. I'm gonna put in my 1s electrons, 1 then 2. I'm gonna put in my 2s electrons, and then I move on to 2p. And it does matter that it goes right here, right? It goes in the first one. You fill them in order. So my 2p electron goes right in my first orbital, and it's got to have the positive spin state first.
So the lines represent like the orbitals.
Exactly. The lines represent the orbitals.
Okay, instead of like 6.
What'd you say?
That's why there's 3 instead of 6, because 2.
Yeah, exactly. Okay?
What if we went to the D's?
Yeah, okay, we can try one of those.
Because the one you showed us right there has all the things.
Right. If we went into the d orbitals, we'd have to draw 5 lines, because there's 5 different versions of a d orbital.
And then you just do the same thing like you did.
Yep, let's practice one of those. If you had to do an f orbital, yeah, you'd have to draw 7 for that, but I won't ever make you do that. Okay, let's go cobalt. We just did something with cobalt a little bit ago. Let's do cobalt. Now, electron configuration for cobalt is going to be pretty big, because there's no abbreviating this orbital notation. Right? There's no abbreviating it. So if I'm looking at cobalt, I'm aiming for 3D, 1, 2, 3, 4, 5, 6, 3D 7, right? That's what I'm aiming for. So you can write out the electron configuration if you want, but you don't have to. I'm just going to start drawing my orbitals, because I know in order to get to 3D, I've got to fill all of them before that. So 1s orbitals, I'm going to go ahead and fill them as I go. 2s orbitals, 2p orbitals, I have to have 3 of them. And I want you to get into the habit of filling them in order. So they're going to get filled. 1, okay, sorry, look up and pay attention to this part, because it's important. It seems like it's not important, I understand that, but it actually is. So as you fill them, you're not going to go 1, 2, 3, 4. You're not going to do it in that order. You're going to go 1, 2, 3, 4, 5, 6. Okay, and I understand that like putting in all 6 electrons looks the same no matter what order you put them in. The reason I want you to get used to filling them across and then coming back is because what if there was only 4 electrons, right? This way you have the pattern and you're doing it correctly. Okay, so I've got 2p filled. Now I move on to 3s. Then I move to 3p. 1, 2, 3, 4, 5, 6. Then I move on from 3p to 4s. And then I can get into 3D. 1, 2, 3, 4, 5. And the label just goes below, right in the middle of all 5 of those. So I'm looking for 7. So I'm not just going to go 1, 2, 3, 4, 5, 6, 7, right? That's not how it works. You fill all the way across. 1, 2, 3, 4, 5, 6, 7. Okay? Right spot, right? We want to have them in the right spot, in the right orbital, because our next step for our next class or next unit is going to be giving that particular electron an address. So we have to know exactly what orbital it's in. And if we put it in the wrong one, then it's going to have the wrong address. Right? We want to make sure we know exactly where it is. Okay, what question do we have about that? Do I have to put the what? Yeah, you do. Right. So you can't just have lines with lines. You got to actually have the line with the orbital label and then the electrons in it. Right?
There's no way to abbreviate them?
No way to abbreviate it. So I won't give you really long ones that you have to do orbital notation for. Cobalt might be about as long as it gets. I won't make you do really, really long ones for orbital notation because I know they're kind of long. Okay? Let's try the last one here on your own. Let's try the next one on your own. I have fluorine this time. Okay, try that one on your own. So that means if I'm going to look at my orbital notation, I'm going to draw my 1s orbital, my 2s orbital, my 2p. So 1s gets 2 electrons, 2s gets 2 electrons. Then for the p orbitals, I'll go 1, 2, 3, 4, 5. Okay, so that's what it should look like. So this electron right here is the last electron that's placed in fluorine. Okay, if you want to write it out, your electron configuration, 1s2, 2s2, 2p5, right? It follows right along. They mean the same thing. They're just represented or drawn different ways. Okay, if you want to write that down to be able to see, in the 1s orbital, I need 2 electrons. Each of these single arrows is a single electron. Right? A single arrow is a single electron. And then tell me, what do the up and down represent?
Whether it's up and down on the orbital.
Okay, remember what I say, the positive or negative, what did that represent? That represents their spin state. One of them has to spin positively, one of them has to spin negatively. Right? That it has to do with their spin state. Okay.